Our next topic is multiclass classifiers. So this refers to the situation where the labels, which are the possible values of your outcome, y, instead of just having two values, it can have k values, where k is bigger than 2. And those are called either the labels or I think sometimes in statistics these are referred to as levels. So you'd say k levels. I don't know. This is just local. These are just local dialects. And we're going to assume that the label set is going to be just the integers 1 through k. So we would refer to these as label or classes. So you'd say class 3 means whatever. It could mean elephant, could mean orange, could mean fraud. I don't know. Class 7 means something, like it could mean Tuesday, or I don't know. Doesn't matter, right? So that's the idea. So we're talking about a case where instead of just guessing yes or no, true or false, fraud, not fraud, this kind of thing, it's more nuanced, and you're actually making a guess among several, more than two choices. Okay, so now a predictor is going to be a function, f hat, that maps from Rn, so it takes in the feature values, that's the vector x, and returns actually just one of the numbers, like 3 or 7 or capital K or 1. And by the way, this corresponds, to a partition of the feature space, because you can simply imagine the sets of points which are assigned to one of these values. That'll be some region, and so some people refer to this as the predictor being it partitions the feature space into the place where you make the different guesses. Okay, now if I have a given predictor f hat and a data set, my confusion matrix is now k by k. It's not 2 by 2 as in the Boolean case. And in this case, we'll get to what that is, but it's just a bit more complicated. And of course, in a lot of applications, some of these off-diagonal entries may be much worse than others, right? So that's actually one of the things that would come up. Okay, so what are some examples of multi-class classification? Well, here's an obvious one, is just handwritten digit classification. So basically, I give you an image of a digit, and you have to guess 0 through 9. So that's 10. That's capital K equals 10. Remember, in our last example, we were simply trying to guess whether the given digit was a 0 or not a 0, meaning 1, 2, 3 up to 9. Here's one: marketing demographic classification. So we would have our, some standard demographic groups, let's say 60 of them. And what I would do is I would look at some purchase history or some other data about a customer or a person. And then I would guess. I'd say, my guess is they are in group 12. And, that means something, right? Okay. Disease diagnosis, when when you're doing more than just trying to say, is this one disease present or not? So you would have a bunch of candidate diseases, including usually if one label is simply there's no disease, right? So and here X, the feature vector, would include test results. It would encode the symptoms of the patient, maybe some history of the patients, maybe even some of their past treatments, this kind of thing. So that would be, and from that you'd look at it and say, I think this is disease A, or this is disease B, or this is a variant of disease B, or no disease. I think the patient is fine. Okay. Another one would be translation word choice. So here you have a dictionary. You have a dictionary in English, and you have a dictionary in Farsi or something like that. And so, it's easy enough to kind of generate, but there's ambiguities, right? So there's a word in English that actually might have, several different possible words. It's ambiguous in English. In Farsi, it's not. It's like one of these 4 or 5 words. And so what you could do is, given the context of that, like the rest of the English paragraph, say, you could try to figure out which is the right word, right? So one example might be the word bank, right? So in English, that could mean the bank of a river or a bank where money is, right? Or it could be to bank an airplane. Could mean a couple of things. these could be different in another language. In fact, in many languages, these are different words. And so your job in translating is not to simply replace bank with one of these definitions, but you have to kind of figure out which it is. And so this would be a perfect example of a multi-class. Well, if there's only two choices, it's Boolean or binary. But in general, there would be several choices, and it's your job to try to figure out which it is. And you could look through the rest of the paragraph. That's the context. That would be X. And you might find words about banking, regulators, blah, 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 all this kind of stuff, money, exchange rates. And then you'd guess, okay, by bank, they don't mean bank an airplane, and they don't mean the bank of a river. It means a bank where money is, okay, financial institution, right? So something like that. Let's give an example. Document topic prediction. So this would be you'd have new documents or a cache of documents, a set of documents, a corpus, people would say, of documents, and a new document enters the corpus. Could be new Wikipedia page. I mean, it doesn't matter, right? And your job is to assign it to one of 37 different topics. Is it sports? Is it politics? Is it science? I don't know. I mean, it's one of these, right? And that would be the ideas. You would make a guess as to which it is based on some features of it. Could be word count, histogram, for example, right? So that would be an example of that's document topic prediction. Okay, so let me explain how to a way to do this. As with Boolean classification, you will learn different and more sophisticated and honestly better methods to do to do multi-class classification. But the least squares one is not so bad, and it introduces some ideas that will be useful and so on, and it just uses the stuff we have in the class so far. So having said that, though, let me explain how you could do it using least squares. Okay, so this is a very simple method. What you do is you create a least squares classifier for each label versus the others. Okay, so if in fact your labels are apple, banana, right, and peach, right, and you're given, let's say, an image it doesn't matter, right? Then what you would do is you just like we did with the digits, the MNIST digits, we would build a classifier that tries to predict whether it's an apple versus a banana or peach. We would build a second classifier that attempts to say whether it's a banana versus an apple or a peach, and then finally one that attempts to say, is it a peach versus an apple or a banana? Okay, so you build three classifiers, one separately for each of the labels, which attempts to detect that label versus the others. So that's how that would work. By the way, there's several things you could do then. One is actually to do things like I'll say that the way that works best with least squares goes like this. We actually don't use the hats, we use the tildes. Now remember that f hat is either -1 or +1. So f hat equals +1. So f2 hat of x equals -1 means I don't think it's a banana. I think it's an apple or a peach. That's what it means, okay? But we'll actually work with the precursor of f hat 2. We're going to work with f tilde of x equals -0.1, okay? Now, there's a lot more nuance in here because if this were like -1 or -0.9, we would have said, well, that's definitely not, that is not an apple or a peach, and we're pretty certain. But -0.1 means you're like, could be. I mean, if you force me to make a decision, is it a banana or an apple or a peach? If you force me to, I'm going to say it is not a banana. But this says that your confidence is not high. So what we're going to do is we're going to evaluate that number, the precursor to the actual prediction, for each of the different classes. And then I have to explain this notation, argmax. So you know what the maximum of a set of numbers is, right? So the max of A1, A2, A3 is just the largest of the numbers, okay? And it's a number. Argmax gives you the index of whoever is the largest, right? And by the way, if there's multiple that attain the largest, then it's not, you just choose one. Doesn't matter which one. Okay, so what this says is super interesting. It says you query, for each label, you query your classifier and you get f tilde. sub L, right? That's a number, right? If it's like really close to 1, it means that thing is really confident that the thing you're looking at is class L. If it's really close to -1, that thing is really confident it's not. Okay, but if it's 0.3, it means maybe, I don't know. If it's minus 0.6, it's somewhere in between and all that. So what this does is it simply says, look at the one that has the highest. If we think of F tilde as being sort of the confidence in our guess that it's positive, this says find not just the one that's positive, but the one that has the highest confidence in being positive. Right? And that's what this says. That's how you guess it. So for example, if I have an x and f1 tilde is minus 0.7, f2 tilde is plus 0.2, and f3 of x tilde is plus 0.8. Well, first let's analyze that before we make a decision. And we'll use these labels up here. So the first one says that if you pose the question, is this an apple or is it possibly a banana or a peach? This says, I don't think it's an apple. And it's pretty certain. It's basically saying, pretty confident, saying like it's not an apple. So, okay, that means probably it's a banana or a peach. Okay. This one is interesting. That says that if I ask you, is it a banana versus is it an apple or a peach? It's basically saying, maybe. Yeah, maybe it's a banana. Sure, maybe it is a banana. I don't know. And then you say, well, how confident are you? And you say, well, a bit confident, not horribly confident, but a bit confident. That's what the 0.2 means. Then we go to f3 tilde of x, which is plus 0.8. Now the meaning of that is we've queried our classifier and we've asked for this x, does it represent a peach or is it an apple or banana? And this thing says, oh, that's a peach. That's what 0.8 means. It's a high number. Of course, when you take the sign of it, you would get f hat 3 is plus 1, f hat 2 is plus 1, and f hat 1 is going to be minus 1, right? So, I mean, that's why this doesn't give you enough information to really make a good guess, right? I mean, you can guess it's not an apple, but you don't know if it's a banana or a peach. So what we've really done is we've gone with the guess, which is we have the highest confidence in. And so that's actually going to be peach in this case. So we take f hat of x is this, right? And so this is the idea. It's relatively simple. And, it actually doesn't work too badly, like, at all. So here's what happens if we run this on handwritten digit classification, right? So we have 10 classes, and this is our confusion matrix, which is, 10 by 10, right? And so this is the, we can look at this, like that is the number out of 10,000. This is the test set. So in our test set, there were digits that were really a 3 that we thought were a 1, and there were 18 of them. That's what that means. So here's one where we did pretty good, 0. In our test set, there were absolutely no times that something was a 6 and we thought it was a 3. So the diagonal here, these are, well, not that diagonal, there we go, these here, those are the ones where we did it right? So that's cool. Everything off the diagonal, all the numbers are bad. Let's look for some of the worst, let's see where we did the worst. Or let's find some places where we did badly, if not the worst. Here you go. That's bad. Okay, 80. And so let's see what that's about. Well, that's a time when the digit was a 9, but we guessed a 4. Now, that's completely that makes perfect sense. By the way, humans would make that mistake too, right? There'd be a lot of times when it's a 9, but it's really a 4. So that kind of makes sense. I mean, these things make sense. If you look at some others where we did poorly, it would be, confusing a 9 and a 7. I know lots of people who make 9s and 7s that look pretty similar. So again, that's kind of reasonable. So this is it. The error rate is around 14%. and it's not overfit because on the training set, you get about the same. That's actually pretty bad. That means that basically 1 in 6 times this thing, basically makes an error on the digit. But on the other hand, this is the simplest possible model. It's a regression model, basically. Which is, not even really appropriate. But it's kind of cool that you get even like 5, that your error rate is only 14%. That's a pretty good starting point. You can't do worse, can't do much worse than that. It means that's a good way to start. We'll only do better. Okay. And so I'll show you just one very simple thing. It's a it's a crazy thing. It's relatively new research or whatever, but I'll show you what it is. Um, Mostly people think of feature engineering as done in a very thoughtful and mindful way. Like you go to an expert and they go, well, I think you should have the product of these features because there's some interaction. You go like, cool, and then you add these features, and of course you don't do it because the expert you do it because, well, you take the advice of the expert, but then what you do is everything. What matters is the only thing that matters is the test performance, right? So how does it work on data it's never seen? So here though, this is something that's come up 5-10 years ago. We're going to make random features. So here's what we do. We're going to take 5,000 new completely random features. We're going to generate a random 5,000 by 494 matrix, and the entries are plus minus one. That's it. Just we flip a coin and we fill out this matrix. Then we form Rx sub j and 0, the max of it, right? So this is crazy. It is utterly uninterpretable. It means absolutely nothing. It's very much like actually a neural network, which is something you may have heard about and you certainly will hear about in other courses. Okay, so that's just random features. And now instead of 494 features, we've got 5,494 features. Okay? Now when you do this, you get a training set error that's about 1.5% and a test error that's 2.6. And you can do better. If you start crafting weird new features, not weird new features, but features that are actually, that kind of make sense, you can do better. And the current state of the art is like, it's like almost perfect. In fact, the current state of the art is that these things can be recognized better than people, which is kind of weird. You might ask, like, what does that even mean? And they do have a way of checking the ground truth, right? That if you, for example, suppose people say, no, dude, that's a 9. And this thing says, that's a 7. Then the way you can resolve that, of course, is by context. These could be zip codes, and one could not make sense, and the other does make sense, and stuff like that. But nevertheless, it's very cool. And by the way, at this point in the course, what it does is it shows you that this just demystifies a lot of these things. If you didn't know about the stuff you know in this course so far, I don't even know how you would think that's done. How does a camera look at a handwritten thing and tell you what it is? And now you know at least some of the methods used. People don't use least squares, but they use things that are very, very close to least squares, and in spirit, it's very similar. And honestly, it's a secret. Don't tell other people, but it's not that complicated, right? Least squares is just not that complicated. But again, don't tell people because it makes us look impressive. If most people don't know how this stuff works and that it's not really as complicated as it looks, it keeps our salaries high and things like that. So again, if you're among friends, yeah, you can say, sure, it's not that big a deal. But I'm asking you now, just for all of us collectively, please don't explain to too many people that these things are not they're really just not as hard as they look. Good. So when you add the new features, here's what happens. Well, okay, first of all, your eyeball looking at that confusion matrix tells you you're doing pretty good. You have 10,000 data points, and take a look at this. The number of errors you're making are numbers like 0, 1, 3. That's pretty good, if you ask me. It's looking pretty good. Now, you're still having some trouble here, right? Here are ones you're making a mistake. You're mistaking a 7 and a 2, 12 times. So, but this is pretty good, and it's pretty impressive. And like I said, this was just adding these 5,000 random features. So if you actually add features in an intelligent way and stuff like that, you can get this down to all small digits like zeros, ones. And I believe the current state of the art on test set, just 0, flat 0. That's on this test set, just it's 0, right? On bigger test set, you have to have a bigger test set to actually detect any failure of sort of state of the art methods right now.